first I just wanted to give you a brief outline of what we're going to be covering this morning. So a welcome and overview. Maggie's going to be talking about the SNAMP final report chapter and give us an overview of the Lidar component. We'll hear from Qinghua. He's around for the Lidar technique, some Lidar algorithms, and Lidar products. And then we'll talk about Lidar lessons learned and do a wrap-up and evaluation. So we hope to get this all in. We know we will in 2 hours. That's one of our advantages of doing a webinar as opposed to an in-person event. We are a little bit more concentrated and hope to get it all done in a time frame. If you have questions, feel free to speak up or type your questions in the chat box. So we did just have somebody join us. Can whoever just joined us introduce themselves and what they're hoping to get out of the webinar? Everyone else already had to do that.
Sue Brittings here, Forest Legacy. Looking for basically an update on progress of, integrating data into the other SNAMP modules.
Great. Thanks, Sue. Okay. And so let me just briefly, for the folks who just got on the phone, go back to our ground rules and just make sure everybody ask everyone to mute their phone until they speak and not put us on hold so we don't have music issues. But do feel free to chime in on the phone if you want to, or the chat box if you prefer, because we do want your input and your discussion ability for all of this. And do we have one more person who joined the line? Can you introduce yourself?
Sure. This is Kelly Larvey from FRAP.
Great.
Cal Fire. Yeah.
And is there something you're hoping to get out of the webinar?
Just to get caught up on what the team has been up to.
Great. I think we'll be able to manage that, no problem.
Okay.
All right, thanks. So I just wanted to give just a brief background for a few people, it looks like, who haven't been to some of our events. SNAMP is a long-term partnership. We started in 2007 with the pre-data collection, the Forest Service implementation of fuels treatments, and then post-data collection. We're in our final year, and we're writing up the results on our 2 study sites on the last chance of the Tahoe National Forest. Give you a little arrow there. And the sugar pine on the Sierra National Forest. We have 6 separate research teams, Pacific Fisher, Spotted Owl, the Fire and Forest Ecosystem Health Team, the Spatial Team, Water Quality and Quantity, and public participation. And so we're all going to be reporting out this year, and the goal of these either integration team meetings or webinars is to get your final feedback before finishing off our reports. That will be due December 31st, 2014. And so we had our public participation webinar on April 2nd or 4th, I think, and we did that online in the same format. We got some really good feedback from everyone. We've actually been looking at how to incorporate some of those suggestions in our final report. So thanks to those of you who were on that call. And the purpose for this call is similar for the Spatial Team. We're hoping to catch you up to what's been done and then get any last-minute feedback or suggestions before we finalize the individual chapters. So in this case, it's the Spatial Team chapter, and we have great information for what's going in there. So without further ado, I'd like to go ahead and hand the webinar over to Maggie so she can let us know what she's going to cover and give us some great information. Maggie, are you there?
I am.
Okay, go ahead.
Thanks so much, Susie, and welcome everybody to the webinar. I have here with me myself, Maggie Kelly, co-PI of the Spatial Team, and Qinghua Guo, co-PI of the Spatial Team from UC Merced, is also here.
Hi, everyone. This is Qinghua Guo from UC Merced.
So we're going to talk about, we'll go through this, we'll talk about the plan for the final report, the sort of setting of the stage for the Lidar component, a brief reintroduction, and then we'll get into some of the latest and greatest products and in particular the vegetation map that serves as the real integrator across many of these teams. We'll also talk about some lessons learned at the end that might be of interest to you all. But I'm also interested in gathering throughout this or at the end what is of interest to you and what do you think are the sorts of things that we should include. So we'll start here. This is going to be the overview of our final report, and it follows pretty clearly the way we're going to run this webinar. We're going to talk about, in the final report, the base data that we use and the Lidar data that we use and how we collected it and the field data. We're going to talk about Lidar products that we've created, and these include digital surface model, canopy height model. We'll talk about some of the metrics that we produce and the forest structure products like canopy cover, LAI, et cetera, and then vegetation maps. And then we, in our resource-specific management implications and recommendations, this is a common section for all of the teams. We're going to focus on our lessons learned, and we'll talk about what it means to map using Lidar versus only optical imagery. We'll talk about the challenges that remain with Lidar, and particularly discrete Lidar. These links between Lidar and wildlife habitat. We'll talk about costs and then some data considerations. And that's the tentative outline as of now. And when we get to the end of the webinar, you can see the content that I've prepared and if that meets the bill or if there's other things that should be raised. So that's the basic structure of the final report. If anyone has any comments, I'd be happy to take them now, or we'll move on and you can save them till the end. Great. So hearing none, I'll move on. We'll talk a little bit about the setting of the stage, if you will, for the Lidar component. So SNAMP has always thought about scaling and what would be the framework for looking at these different resources in the Sierra Nevada. And we recognized early that different teams are going to work at different scales, but we do want to have an integrating scale, the fireshed scale, at which we're all comparing results and that we're all sharing products. So this graphic really is just to demonstrate that spatial data allows us to provide information from the individual tree scale up to really quite large regional scales. And that's why the spatial team is a component of this. I apologize for this slide in the transferring up to Adobe Connect. The transparency disappeared, but the gist of it is that each team is working at the scale at their individual scales, but the spatial team is helping provide common products that we can all integrate across in this backy design before-after control implementation. So that's why the spatial team and the spatial team products that we're building are critical. So just to give us an update on some aspects of the spatial team work, this is the spatial team, the SNAMP timeline that you have seen at the last meeting. It gets more and more complicated every year, and this is the timeline that we're working with now. And the Lidar flights are highlighted in bold here. We gathered pre-treatment Lidar flights in 2007 and 2008. The treatments began implementation in 2011. And in 2012, we started the post-treatment flights. We flew Sugar Pine, no problem, in 2012, but we were cut short at last chance by early snow. And so we had to come back in 2013 and refly last chance, which we managed to do before the fire came. So that was the other sort of surprise along the way, was scheduling LIDAR acquisition around things like weather and fire. So this is just a summary. SNAMP begun. We had our pre-treatment field seasons. We got our pre-treatment LIDAR flights at both Sugar Pine and Last Chance. Reiterating what I said in the last slide, post-treatment LIDAR flight at Sugar Pine was completed in 2012. Post-treatment LIDAR flight was begun in 2012 and finished in 2013. And again, SNAMP is going to be complete in December 2014. So it's a really rapid timeline to get this post-treatment data analyzed. And the Spatial Team, and in particular the UC Merced team, has really been gunning it for the spring to get these products done. So again, just to remind everybody, it was a really an interesting time. We got everything in Sugar Pine in 2012 and captured some of Last Chance in 2013, and then this gorgeous fire starts to burn, the American fire. And the good news is that we did manage to get the post-treatment pre-fire LIDAR for Last Chance, and that's what we're going to show you some results from. So just to summarize then, the SNAMP LIDAR acquisition was run through a contract with NCOM, the National Center for Airborne Laser Mapping. The pre-treatment collections in 2007 and 2008 were all discrete LIDAR, 4 returns. You can read all the specs there, but the data is very rich. It's average about 10 points per square meter with very good fidelity and elevation accuracy. This is small footprint information. The acquisition costs, if you're interested, remain pretty stable between the pre and the post-treatment. They're about at $6 a hectare or $2.50 an acre. And again, for the post-treatment, we also contracted with NCOM. So that's how the data was captured. Just a quick reintroduction to the LIDAR technique. We can look at the benefits of remote sensing in a number of ways, and we live in a wonderful time for getting multi-resolution and free imagery about the surface of the Earth, from things like MODIS to Landsat to color infrared and other orthophotography. And these types of data sets are fantastic for gathering information about canopy cover and vegetation productivity, about vigor and phenology and vegetation patterning. We can get repeated coverage, synoptic coverage, and often free imagery, but they don't give us good information about forest structure. And this is I don't need to remind any of you about this. We can't tell much about the vertical structure of the forest that's so important for things like the way animals use the forest and how fire might burn through a forest and how snow might interact with vegetation. And so for that, we do need this LIDAR technology. Again, relatively simple technology, just measures the range, and that's the time it takes for light to be emitted, bounce off a target, and then be received. And from that simple calculation, you can figure out how long it took, and by virtue of knowing where your sensor and emitter is, you can tell how high above ground that target is. And the discrete LIDAR that we're using yields 4 discrete signals per pulse. So it makes for very dense, very rich data. So here are the graphic, as you've seen before. The first return is the first thing it hits in a forest. Often that's part of the canopy. The last return is often the bare earth. And so the LIDAR data is being commonly or increasingly used in forest research from a range of devices. The upper left device is a handheld camera, laser camera, that's increasingly coming on the market. This is mostly for internal, like inside building stuff and gaming stuff. And then the upper right is a terrestrial LiDAR. That's field-based, so it's moved throughout the forest and gives really detailed maps of stands. We did not use either of those two methods. We used airborne LiDAR on, and this picture is shown with a helicopter, but it's often mounted as it was with NCOM on a plane. And again, what discrete LiDAR yields is multiple returns. The strip on the top is a combination of all the returns, which can be decomposed into the first thing the light hits, which is usually the canopy top, the second return, part of the canopy, the third return, part of the canopy, and the last return, usually the ground. And from that combination of those four hits, we can get all kinds of information. That's discrete LiDAR. Waveform LiDAR is newish. It's coming online, and I've mentioned it before. I mention it again because our post-treatment flights actually were able to capture discrete as well as waveform LiDAR, which is useful. So the waveform concept is that instead of returning a discrete point at these key peaks in a signal return, it returns the entire signal. And you can tell something about what the target is, what it's hitting, by the shape of that signal return. You can tell something about the amplitude of the return, the range, the width of the signal. All of these things are key to letting us know what the sensor is actually measuring. So I'm not going to show you any results from the waveform stuff today, but it was captured as part of our post-treatment acquisition. So this is what it looks like for us. This is the NCOM flight. These pictures were taken during the pre-treatment flight in 2008. So that's the plane, and this is the Optical sensor here. Sorry, I'm pointing at it with my mouse, but I don't have the mouse. Here's the mouse. So these guys this is the Optical sensor that NCOM used. And it's very similar to aerial photography. You fly repeat paths, and there's a certain amount of overlap that allows for a really dense mesh of return signals. And none of this would be useful, none of the products that we're going to show you would be possible if we didn't have very detailed field data, and these data were largely gathered by the forest team, and throughout both sites. This is a dense mesh of field sites. You've seen them before, 500 meters apart in most places. The information collected at each of these plots in 12.5-meter radius circular plots are listed down at the bottom of this slide. And as you can tell, this is really geared towards fire measurement, height, dBH, species, vigor, crown class, height to live crown base. These are all measures that, when interpolated across space, go into fire behavior modeling software like Farsight or FlamMap or others. But these are the field data that we use to build regressions to map wall-to-wall LiDAR products. And on the upper right is Marek Jakubowski. He was a former grad student here doing some of the work, and he also took site photography at each of the cardinal directions around the plot center. So the LiDAR data itself looks like this. It's delivered as a giant point cloud, just a bunch of X, Ys, and Zs. This particular scene is from a area of forest that had been burned over in the 80s, and you can see down on the ground, there's lots of downed logs there. Then you can see the individual trees themselves. Here's another snapshot of the LiDAR point cloud. It's given to us from NCOM in this standard product. It's using a LAS compression, and it's basically X, Y, and Z, and some information about intensity and some of the specs on the how it was acquired. And from this point cloud, we can build these series of pretty typical models or depictions. So at the bottom here, we have the digital terrain model, and that's the raster product at very fine spatial resolution that's made from the last returns. We also have the digital surface model. That's the product, raster again, fine resolution, made from the first returns. And the difference between those two products is the canopy height model, and that I like to call is the living or green wedge, really, with elevation removed. And the product that we also have spent a lot of time to talk about is the individual trees. So pulling out individual trees from that point cloud has been very helpful for us in a number of subsequent analyses, particularly with the wildlife team. Okay, so that's the background to the Lidar technique and the SNAMP acquisition of Lidar. Are there any questions about that content? All right, so what I'm going to do now is turn you guys over. Qinghua is going to walk through some of the products that we have made with the Lidar.
Okay, here we show the DM product for both sides. I want to mention that the Lidar data is a discrete point cloud data. So in order to generate the good DM product, we need to choose a spatial interpretation algorithm to generate the surface. So here I list a paper we published in 2010 describing the difference of choosing the interpretation algorithm in terms of generate the DM product. In this paper, we found that kriging is one of the best methods to generate the DM product. And Maggie just mentioned about the Lidar data. If we receive the raw data from ANCOM, and what we're going to get is only the point cloud, which means that basically you have X, Y, Z. X, Y is the coordinate of the point cloud, and Z is the height information of the point cloud. But for us, because we want to get force attributes, not just X, Y, Z, but also include tree height, mean tree height, and DBH, all these different kind of force attributes, which means that we need to use some kind of algorithm to produce those matrices in order to do a further analysis of the vegetation pattern structure, as well as link those products to other forest health team and fire team and water team. So here's list the kind of product that we generate in this project include the mean height, maximum height, diameter at breast height, height to life, canopy base, canopy cover, leaf area index, individual tree density, tree size classes, canopy fill, and biomass. I want to say that most of those attributes will generate through a regression approach, which I'm going to talk about later. Some of those attributes will generate directly from the Lidar point cloud. For example, the leaf area index. They have a well-established algorithm to generate the leaf area index from the point cloud directly. And individual trees also another product that we directly estimate from the Lidar point cloud. And almost all the other attributes we generate from the regression approach, which I'm going to talk about now. Okay, this is the kind of an overview about what kind of matrix, the Lidar matrix we use in the regression approach. So if you look at on your right here is the list of Lidar matrix. It includes the height information. Think about look at the images over here. You can think about you put a slice through all the Lidar point cloud, and you get some kind of attribute within that specific piece of information within different heights. And you can calculate the average point density and maximum point, and standard deviation, skewness, kurtosis, and all these kind of different attributes you can get from this slice of the point cloud. And use those information, you treat them as independent variables. And the dependent variable is the point that Maggie just mentioned from the forest health, as well as the spatial team with georeference the POC data. Remember that a lot of time when particularly the field team, when they went to the field to collect the field data, the GPS coordinate is not precise enough or accurate enough to do this kind of analysis. Because in Lidar product, we are talking about at the resolution of 20 centimeter. So which actually America, former grad student from Maggie's lab, he spent a whole summer just want to georeference those POC coordinates. And so then all the other attributes we get from the forest health team, and then we do a regression analysis between the Lidar matrix and the dependent variable is those forest attributes I just mentioned. And here's the kind of algorithm describes how to derive the leaf area index from the point count directly. You can count how many points you hit the ground, how many points you hit the vegetation, and then calculate the gap fashion, and using a well-established algorithm to estimate the leaf area index. Now, we have other projects which include how we divide the individual tree and include some visualization things that if you're interested you can send me an email, and I'm more than happy to describe that. But due to the time constraint, so I'm going to move to the vegetation mapping because we think that that's something you'll be more interested in. Okay, so the mapping the vegetation, we use three different products to map the vegetation. First is the Lidar data. Again, we use the Lidar matrix. 0 percentile is kind of the lowest point, and 100 percentile, and 1 percentile, 5 percentile, 99 percentile. This is the Lidar matrix we use to map the vegetation, and we'll also include a canopy cover, tree height information, and some elevation information, include the DM, slope, and aspect. Together with Lidar data, the area images, the NIP data will also use to map the vegetation. That includes the RGB bands from the NIP data and also some textual information such as the mean, standard deviation, and homogeneity, etc. Those information we can get from the area images. To validate our result, we also combine the POC data too in the vegetation mapping process. So here is the kind of overview about the algorithm we use to map the vegetation. The first thing is, since we have so many features from aerial images as well as from the Lidar data, so we need to do kind of a feature extraction to kind of compress the image features into only like 3 components here. So we first compress the area images, because even though I look at here 1, 2, 3, 4, 5, 6, 7 bands of feature from the area images, but since we have RGB like 3 bands, therefore we have 21 features just from the area images alone. Also the Lidar around the same magnitude in terms of the features. So we need to compress those features. So the first step, we use the principal component analysis to convert the different features, all the features, into only like 3 components, which represent 98 of the variation of the total variation. And then similarly, we also use the principal component analysis to compress the Lidar matrix. Also, with the first 3 components, we get a 98 variation already. And then we combine those 6 components together, only 6 components, to do our vegetation mapping. And because different teams have the different needs in terms of the vegetation products. Some teams only need a wall-to-wall vegetation map. So for those kind of needs, we use classical core pixel-based algorithm to map the vegetation. some team like the forest health team and fire team, they need this kind of a polygon into the fire model. So we use object-based classification. So basically, how we treat the pixel, when we treat them pixel by pixel, when we treat them by object-based, which means we segment the images first to generate this object, and then using some kind of a classification algorithm to generate a map. And finally, we're using a prop data to validate our result, as well as first to train our algorithm as well as the validate result. And here's this figure actually generated from John Battle here. He used the prop data to validate the vegetation mapping result. I want to mention one thing, that because in these two sites, we're on purpose to choose, at the beginning of this project, we're on purpose to choose a relatively homogeneous forest. So mapping the vegetation in these two sites actually become pretty challenging because the difference is not that big. But even though with our algorithm, we can get a pretty good result. Here's to show you the slight difference among different class in the future space. You can tell that different vegetation class, you can see they can distinguish from the primary axis and the secondary axis from the prop data. And this is the result that's showing the pixel-based vegetation mapping. And we have the sugar pine and the large chain site, and we have the different classes. For the sugar pine, we only have 4 classes, and the large chain we have a little more than 4 classes. It's about 7 classes. And as I mentioned, for the forest fire team, they want the polygon. They don't necessarily want the pixel, since to run the fire model, the polygon is the kind of unit for them to run the fire model. So then we also try to use the object-based approach to generate this kind of polygon. Again, all this polygon is generated by combining the Lidar and aerial photo together to generate this kind of polygon, with consideration about both the vegetation attributes as well as the DM attributes. And after we get the map, we also need, because we have a pre and post treatment Lidar data as well as the aerial photo, so we want to get some kind of a change detection result before and after forest treatment. Here's the kind of describing what kind of algorithm we use to get the change detection result based on the Lidar product. I mean, I don't want to read through the text here, but just look at the figure here. You can, the flow chart here, you can see the method we used. The first is we use the pre-treatment Lidar data, and then we generate a pre-treatment canopy cover. Similarly, we use the post-treatment Lidar data, we generate a post-treatment canopy cover. And we take the difference between these two canopy cover. If we have a forest treatment, so we will assume the forest canopy cover will decrease significantly. And then we use those kind of information to inform the algorithm to say, oh, this is a change or this is a no change. And again, we apply both the object-based approach as well as a pixel-based approach to get the change detection result. And this is the result just showing the change detection. And if you look at the figure over here, the green polygon is the treat area. This area is provided by the U.S. Forest Service. Again, when we run this model, we actually don't have this treat polygon. We just do our Lidar change detection, and then later on to overlap the polygon on top of our change detection result. So the red area is derived from the Lidar. It's based on the canopy cover, the change of canopy cover. Also, I want to mention that we have also tried different other algorithms in terms of detecting the change of the vegetation from Lidar data. But most of the algorithms give us a pretty consistent result. And the blue color here represents the unchanged area. As you can see, the treat area and the change area detect from the Lidar, they agree pretty well in majority of area. But we do see some discrepancy that we would like to investigate later on particularly in this summer, we want to go to see why we see some change in certain area, but from LiDAR, but we do not see it from the data provided by U.S. Forest Service. Overview, we look at the total accuracy is about 95%, and the cover coefficient is about 0.78, which is considered pretty good in the field of remote sensing classification accuracy assessment. Okay, so this concludes my part. Is there any questions? If not, I'm going to pass it to Maggie, and then maybe we can answer the question in the end of the webinar. Thank you.
Great. So you've seen a little bit about the vegetation products that we've made and this important vegetation mapping component. And that's what I wanted to talk about next, is the ways in which these products, and in particularly the vegetation map, is being used across SNAMP. So if we look at the products first, we've got a list of these classic wall-to-wall maps from LiDAR, including DEM, but also these vegetation products that you've seen before. And I'll just quickly go through how they're all being used across teams. So the DEM and these vegetation products that deal with structure have been used and are being used by the FFEH team in their fire behavior models. The water team is interested in, for their hydrologic modeling, RESIS, which I actually spelled wrong there, so forgive me. They're interested in the DEM, the canopy cover, and leaf area index. Those are the critical layers that drive their model. The OWL, because with at least the pre-treatment data, we don't have a lot of coverage over the OWL sites, but we have been using the canopy cover and individual tree location to understand nest tree characterization. With the Fisher team, we've done some neat work looking at denning trees, because we do have more Fisher, or more locations, more data about Fisher locations. So in the paper that we worked on with the Fisher team, we used topography data as well as height data, canopy cover, and individual trees. And then the public participation team, we've been making use of all of these maps and others as well in public meetings. So these products have shown up in the teamwork across SNAMP. And if you want more information, all of the publications from SNAMP are on the SNAMP website. But the key...
And Maggie, I'm sorry, this is Susie. Before you move on, could you go back a couple slides and just address John Buckley's question, which was...
Oh, beg your pardon, John. I didn't see that. Great.
Individual trees and canopy fuels, what those are.
That's a good question, John. So the individual trees... That's I think there's an echo, but I'll carry on. So the individual tree layer has to do with a method that we derived to pull out from the point cloud the individual trees. So you have a layer that has an X, Y, and Z location, basically a location and a height of the tree as well as its crown size. So it's a really useful layer. We've been using it in a range of ways to look at wildlife and other aspects. The canopy fuel is a layer that's specific to the forest fire behavior modeling, and we've been working to connect the LiDAR metrics with canopy fuel estimations. That is not actually a really solid fit right now. We get good fits between general fuel classes, shrub, timber, etc., but we don't get good fit with specific fuel classes. So the forest team is actually not using the LiDAR-derived canopy fuel in their fire estimations, fire modeling, beg your pardon. Does that answer your question, John? Great, thanks. Okay, so again, the details of all of those ways in which we've been using these products are in the publication. Measures of pixels. So before I move on, Craig has asked a question. Can you talk more about measures of homogeneity, pixel similar to the next pixel? John, Craig, do you want to provide a little bit more information about that? We actually don't have any products that look specifically at heterogeneity. We could. It's a fairly easy thing to do. Each of the raster-based products that I mentioned have some measure of spatial structure. Qinghua wants to chime in on that.
Well, I'm not sure if I understand the question. The pixel similarity, if you talk about the vegetation mapping, we do use the pixel similarity to group the pixels together into objects for the vegetation mapping. Yep. And you can answer the question, or if you need more clarification.
Oh, great.
Okay.
That's
yeah,
what he. So, do you want to? So that's great. So the object-based approach that Qinghua talked about is definitely looks at pixel homogeneity within a object. So it's basically it's similar to a region growing approach, where you look at like pixels in your immediate neighborhood, and there's a threshold between how similar you are to your neighbor versus how similar the object is to its neighbor. And there's ways of thresholding that. So the vegetation product that Qinghua is talking about uses that object-based approach. Does that help? Okay, great. Thanks, Craig. These are great questions. So I wanted to talk more about the heart, the focus of the SNAMP integration, which is these vegetation maps. So we've had a number of all-hands-on-deck science team meetings that think about this process. And this you've seen before at our last public meeting last year. And this is the workflow that we've agreed on across the SNAMP science team to develop an integrated assessment. And it all starts with the Lidar data. So the workflow is we get raw data from NCOM, we process it, we're including NAPE imagery and plot data, as Qinghua outlined, to get a Lidar-derived vegetation map. That map then drives the fire behavior modeling that the FFEH team is busy working on right now. They've completed the last chance work, and they're working on the sugar pine. So the outputs of that vegetation map in terms of fire behavior and fire effects are then given to each of the other teams. They're given to water, to wildlife, and to FFEH. Each of those teams, in turn, have their own way of interpreting and using that fire, the output from the fire behavior models. So the water team is relying on this rhesus model, as I mentioned before, and so they're looking at the ways in which fire effects will influence vegetation measures that go into rhesus. The wildlife team has their own way of looking at these things, and at the IT meetings coming up, they're going to talk in detail about them, and they're mostly concentrating on fire effects, is my understanding. And then similarly, the FFEH team is going to be looking at health metrics, forest health metrics, as a result of these fires. And again, the fire modeling is run with and without the treatments. And the goal behind all of this is to have at the end an integrated multi-resource assessment of the impact of splats. And at the heart of it are these vegetation maps that I showed you before. Are there any questions on that? I know several of you actually this was the key part for your information, so we can pause here if there's questions. Okay, great. So I'll continue on. So I would like feedback if you have it here on this part. Hold on a second. I'm getting a question from John. How does the wildlife team compare the assurance of an outcome from a forest treatment compared to a possible unproven outcome from a possible fire in the future? It's a great question, John, and I would not be the one to answer it, honestly. That's something that we can take note of and send to the PIs of the OWL and Fisher team and make sure that they address this question in their IT meetings. Great, thanks. So these are the sort of lessons learned, what we've thought about as we do this work. And I've picked 6 topics here, and I'd be interested in feedback on these. The first is, SNAP's really been this gold standard. It's gotten all this data, this Lidar stuff. What happens if you don't have that? How much can you get away with just optical data? So I'll spend a little time on that. There still are challenges with Lidar. It's not perfect. There are some things that it doesn't do well, like mapping understory, particularly in dense forests. I'm continually struggling with this links with wildlife because it's great to capture, Lidar does a really good job capturing structure, but what do these metrics really mean ecologically, and what do they mean to managers? Then there's the cost of Lidar. I've put together a little bit of an analysis about that. We've also done some work looking at how much you need in terms of density of points, because Lidar data really can get very large, very fast, and that can be a challenge. So we'll just go through these. This is this first point about forest attribute estimation, and I have here a table and a list of these products that we've created, and then what you can expect to get from just optical imagery, such as freely available Landsat and high-resolution things like NAPE, because if you're looking at the past, you can't use Lidar. That's a real challenge. We'd like to time travel, but we can't. So if you look at this table here, we've got the dark checks are where we really feel confident that we get good, accurate products from Lidar or from the sensor. The lighter checks are where it can still be done, but it's done with reservations. And then the asterisks mean where we're not really directly measuring things, we're really building regression relationships. And so the Lidar really does a good job. Mean height, max height, very well. DBH does a good job as a regression from those previous measures. Height to live canopy base, again, does a good job with canopy cover, good job with individual trees, leaf area index, tree density. Doesn't do a great job with canopy fuel yet, or we haven't. There's papers that say it does better, but we haven't managed it as well as them. Biomass does a good job too, again, regression-based. And if you look at Landsat with some reservations can get information about mean height, max height, DBH, canopy cover, leaf area index, something about fuel and biomass, but really does a poor job getting at height to live canopy base, individual trees, tree density, these kinds of things. Optical high resolution NAPE, again, does a okay job. You can get information from about height and DBH, and you can do a really good job getting canopy cover because of the high resolution, and does a somewhat okay job at individual trees, leaf area index, tree density, canopy fuel, and biomass, but again, very poor to the structural things like height to live canopy base. I think all of these really are not open to debate. I mean, this is my first cut at this, and I'd be interested in feedback from you. Sue has a point. Van Kane and others use Lidar to develop a vegetation classification. Open, sparse, shorter, multi-story, top story that they are using to evaluate structure and gaps and clumpiness. Any plans to create a classification based on structure might be useful. This is a great question, Sue, and a great input. And I'm going to get to this when we talk about the point, I think it's point 4 about wildlife, so I'm going to address that when we get to it. So, and again, hold on, I'm just getting a comment here. Okay, so the point number 2 is that LIDAR isn't perfect, especially discrete return LIDAR is not perfect. Some of you have seen this graphic before. It's a cartoon of a forest stand. The bars on the left indicate the correlation coefficient, the R squared, between a suite of LIDAR and the field plot data. And as you can see from looking at those bars on the left, as you move down through the canopy, you get poorer fits. And that's really to do with the fact that a lot of the energy is used in the top of the canopy, and sometimes you don't penetrate down with enough energy to sense the shrubs. So things like shrub height, shrub cover, fuel loads, they're really poor with our discrete LIDAR. So we found in a paper done by Merrick and others that the fuel types, shrub, timber understory can be predicted reliably, but specific fuel models are really difficult. This gets back to, I think, John's question earlier. And the accuracy of these regressions decreases as you move down through the canopy. What we have to say about that is that's true, and we're investigating what Waveform can do because we get the entire signal back. You get that full return back. And so Waveform has been shown in a number of papers that it does a better job of getting at understory. And there's a lot of exciting things that look at waveform data and wildlife. And just so you know, there's our last chance footprint. The red is the pre-treatment coverage, and that big blob down below is the post-treatment recollection that has discrete and waveform. So we're hopeful that we'll be able to say something more about this. Okay, point 3. I think this is a big one. So LIDAR captures structure, but what do these metrics mean in terms of field data? What would be a good proxy for structure that's important for wildlife and that you can get in the field? So we did this paper with a postdoc and the Fisher team, and we got good correlation between LIDAR metrics like kurtosis of points and Fisher-Denning trees. But what does that mean for managers? What can managers see in the forest that can be measured that we can then relate to LIDAR? And I think this is what Sue's getting at in her comment here. So they did, it sounds like a simple classification, open sparse, shorter, multi-story, top story, to get at vegetation structure and clumpiness. And again, this is what the GTR 220 talks about too in terms of forest structure. Can we use LIDAR can we pull from the LIDAR simpler measures that mean something to managers that can be measured in the field? I think that's a really important area that I'd like to continue thinking about. Sue, does that help? Or does that address?
Yeah, sure. Only, trying to think about, I've yet to decide how successful their classification was, but that's, in my mind, when I heard about it and then read a little bit about it, it seemed like that was, it was going to provide some utility for wildlife. No one's taken the steps then to see what those, how those types relate to wildlife use, but it just struck me that, for instance, the Fisher data set is so rich.
I agree.
That being able, if there was some interest in creating those a classification, like a structural classification, that could be quite interesting. I went back and looked at your veg map, back, like a third of the way through the presentation there, and that vegetation map there had some, probably had some connection to the structure classes, but it was blending in species composition at the same time. So forest types plus structure came together in that classification.
It's a good point. I'm going to take note of it. I want to keep working on this link between LIDAR and wildlife, and I think finding some sort of proxy for structure that makes sense from a LIDAR perspective, from a wildlife perspective, and from a field perspective is key.
Yeah.
Hey, Maggie, this is Carlos. If I can interject for just a second. Van and I have been talking about this very thing for quite a while now, and now that we have numerous samples, particularly over large areas in the Sierra Nevada, I think we're at a point where we can actually develop some sort of new generation classification that gets at more of these complex structures that people are interested in. And right now, the classification is based on a hierarchical cluster analysis, drawing random pixels from within the LiDAR footprint, but each one has been done independently to date, and we're at a point where not only do we have the data, but the computing power to actually do some broader classification.
Yeah, this is Qinghua. I completely agree with you. I mean, it's kind of, we're just working on a paper now to describing the change detection method we developed. And we found that in the literature, actually, there's not many papers talk about how to use the LiDAR to do the vegetation mapping. So I do see they have lots of like a new research area and as well as application area with those kind of data. And also the computation power is another concern that we're actually dealing with now because this huge amount of data. We are just to the point to process the waveform data, but the waveform data alone, just one site, where the data we get is 2 terabytes. The whole waveform data for the whole tower forest is about 12 terabytes of data. So it's a very huge data set that we have to deal with. And all the methods we developed so far is based on parallel processing and utilize multiple CPU. Otherwise, we won't be able to finish such a big footprint in order to calculate those kind of measures. So I think it's many interesting questions that we can work on in this area. Again, back to Sue's question about the forest structure, another very good comment and interesting suggestions. Yesterday we also talked about for example, now we can use this kind of canopy structure to detect where is the treated area, particularly in the sugar pine area. Then what we can do next is we try to link those structure information to such a rich data set from the feature data. Then we can see is there any correlation between the structure information with the change of the habitat in the feature area. But again, we're just getting started to processing all the LiDAR data now. We just finished the product, so it's the next step that we want to work on in the future to link those structure information to actual feature and fire and forest health applications.
Just one other thought is I was just thinking a little bit more about Dan's what I saw of the work they were doing. They didn't. They left species were unaddressed in their classification system, and so I thought it was interesting your use of the aerial imagery, the 3 bands in the imagery to try to extract out species. I'm guessing that's where you got the species composition, or was that from the plot data?
Yeah. So let me explain that. The reason we see the literature use LiDAR to map the vegetation. We also, in the past, everybody used the aerial photo to map the vegetation. But now we found that combine the both provide the best accuracy in terms of mapping the vegetation species. I want to make a point that the species composition result is through the post-classification approach. We don't use those kind of attributes in the segmentation. We just put a segmentation based on the LiDAR and aerial photo, and then label them based on the PROC data. So the PROC data used to train the classification result is not used to in the classification like the segmentation or the pixel-based approach before we do the segmentation. So it kind of post ad hoc analysis.
Great, thanks a lot. John is typing something, so I'll wait to hear what he's got. This is really terrific, you guys. Thanks for your feedback. Well, I'll move on. So I do think that LIDAR and wildlife connection is really important. John wants to follow up. One proxy for important structure for marten and perhaps fisher is size and abundance of large snags and large down logs. Are those now being considered? So we did look specifically at the use of our discrete LIDAR to map down logs, and we picked an area where it should be pretty easy because it had been burned over and you could actually see the down logs, and we had moderate success. But mapping down logs throughout the forest where there's a real dense overstory is challenging. We don't have a lot of information Qinghua's giving me a pencil. We don't, it's hard to do. And so we actually don't have a product that looks at logs and snags. But, as Qinghua reminds me, there has been some promise using waveform because you get that full signal, and the shape of the signal from the ground can be useful to understand more about the target. Great. So thanks for that feedback. So the point 4 is LIDAR and costs, because a lot of times people are thinking about costs, and so there's not a lot out there in the published literature about costs. There's a couple papers I found that estimate, Wolder et al., Wolder's one of the key LIDAR scientists, he estimates a cost of about $3 per hectare or $7 per acre for mapping with low density, so that with the SNAMP, we come in a little bit under that. And Randolph Wynn in 2006 estimated that you could do the field collection and analysis at about $34 a hectare, which is, I'm just putting it out there for you guys. And we can compare it to what it costs for Landsat, which is now free. But what we're dealing with now is sort of comparable to Landsat around the 1980s. That was the standard for vegetation mapping.
Yeah, one thing I also want to add is that in addition to the cost, the power of LIDAR actually can devise something that is impossible by other products. Let's take an example about our change detection result. If we use an area photo, because we really just treat the area with a not substantial change in the landscape, we actually can see much of a signal based on the area photo. But the LIDAR can tell easily that which area has a canopy like a structure or canopy cover decrease. So it's not just about the cost, it's also about the ability to map the vegetation as well as the accuracy. A lot of time when we saw the previous slide here, we saw other products like a TN and NIF data can divide the similar products, but the accuracy is much lower than what we can generate from the LIDAR products. Particularly in a project like this, because we want to detect those subtle change before and post for treatment. If we're using the area photo or TN data, I mean the data alone will generate much bigger area than the signal we want to detect.
That's a great addition. Thanks, Qinghua. So the fifth point also refers to cost. We were curious about this idea of what is the trade-off between cost and density with LIDAR data. And if you look at this graph on the right, the turquoise line that's horizontal represents if you have a fixed cost that you can spend. And the more area you cover, the less density you're going to be able to get away with. So in other words, if you have a fixed cost, you'll cover less area at higher density. And the green vertical line is if you want to cover a set area, your costs increase with density. And so that's this sort of classic trade-off in LIDAR data between cost, area, and density. And so we wanted to investigate how much was enough. And so we used all our plot data and looked at all those regressions across multiple pulse densities. And here this graphic depicts our SNAMP LIDAR data from 9 pulses per square meter down to under 1 per square meter. And interestingly, when you look at plot scale data, you know, if you're just really trying to get a broad scale mapping of forest structure for something like fire behavior modeling, the accuracy really plateaus at about 1 pulse per square meter. Doesn't get a lot better. And that's very promising if all you need is to get this plot scale work done. If you need to get individual trees, however, you have to have the high density. That's critical. But there could be cost savings here if all you wanted to do was do wall-to-wall mapping of these, you know, sort of broad-scale vegetation classes. And indeed, many states in the U.S., like North Carolina, do a low-resolution 1 pulse per square meter mapping of their entire state because you can cover a lot more area if you go less dense. And the final point is just about the size of LIDAR. LIDAR can get pretty big pretty quick, and Qinghua and Carlos have both touched on this. So a forest stand of about 5 hectares or 12 acres in size. I'm just showing you how it's represented with the typical remote sensing suspects, with Landsat TM represented by about 55 pixels, ETM 200 pixels, Spot 500 pixels, Iconos 50,000 pixels, and all those, that really pales in comparison to what you get with the point cloud. You're at about 200,000 points up to 2 million points depending on your needs. And so these things really can increase quite quickly, as we have all experienced working with, and as you guys have as well. So Ann Lombardo has a question there. How well does LIDAR identify snags? So these are standing dead without a canopy. So Qinghua is going to address that.
Yeah, I think actually if you're using LIDAR data, particularly with the waveform data, I would say that it's pretty accurate to get the snags. Although we have not tried to implement our algorithm wall-to-wall, but we do using the LIDAR data to check the snap structure as well as healthy vegetation structure. They look very different. So we are optimistic that we can match the snap with a very high accuracy, which again is another benefit of LIDAR. There are lots of things that when we detect the snag compared to the aerial photo won't be able to see much snag compared to the LIDAR. So I would say they're very promising.
Okay, and then just finally, we're wrapping up here just to make a mention that we are curating all of the data from SNAMP, and all of the data will be transferred to the Forest Service after the project, but it is maintained right now at the UC Merced server and will be maintained for a year after the project. So that's all we have for you. We have time if there's outstanding questions that haven't been raised in the chat or on the phone. We're eager to get your feedback.
Thank you, Maggie and Qinghua. That was really great and very comprehensive. I feel like I learned a lot. We do have plenty of time if people have additional questions or want to pursue some of the earlier concepts that were discussed. So go ahead if you have a question.
This is Craig. Hopefully I can talk better than I can type, but I wanted to go back into the homogeneity, heterogeneity, and the grouping of pixels. And I know there's the more challenging understory information gathering. But I'm wondering, are those groupings of pixels that are looking at similarity and dissimilarity, are those then rolled up to a scale that tries to communicate with, say, Fisher researchers like Craig and Catherine, who are taking plot information, understory information for Fisher and OWL potentially to understand OWL and Fisher use better in the understory? that to me is the place where we still struggle to figure out what's going on.
It's a good point, Greg. So the polygon layer that we mentioned and showed before has one use right now, and that's to feed into the fire behavior modeling. So it hasn't been used across teams in other ways, but it could be. And so I think that's an important note that we could pursue seeing if that polygon layer that depicts structure might be of use to the Fisher researchers. But we have not thought of it that way up to now.
Yeah, so again, if you talk about the understory, since we have the waveform data now, I mean, there's something we really want to look at as next. I mean, they have many vegetation structure information we can derive from the Lidar data, particularly with the arrival of the waveform data. But again, we need to work with the individual team to try to identify what is the best structure information that would potentially link to the fisher habitat, our habitat, as well as the other teams. So we will take a note on this question. So
yeah, I think we should follow up and think about this because it's not something we actually have thought about. So that's a good addition.
And Maggie, can you just clarify for us? I understand from your presentation that you did acquire the waveform LiDAR, but
Correct.
Is that actually something that's going to be analyzed as part of the SNAMP report due in December?
Yeah, no, we actually we have discussed this during our annual meeting, and because we have the very tight schedule now for generate the report and the products for the end of the final for the project report. So we do not analyze the waveform data yet for this project. And I also want to mention that this is a kind of new thing to the whole community, the waveform data. Particularly ANCOM, also the first, I won't say they're the first time, but they actually, when they generate those data, we found a lot of problem with the data yet. Georeference is one issue, how to georeference the waveform data with the discrete LiDAR together with other products. There's not a very challenging question there. I think we figured out the algorithm to do that, but still, there's still a long way to go to finish those products. We need to continue looking for funding to do a further analysis on those.
Yeah, that's helpful. So just to clarify then, it's something you're going to be working on after December 2014, probably.
Probably.
Great. Thank you. Other questions from anyone on the line? Well, it sounds like you answered everyone's questions already, Maggie and Qinghua, so thank you so much.
I really appreciate your feedback, and if you have other things that come up, feel free to email us. And go to I put up the last slide is the other integration team meetings that are coming up. So those questions that were specific to the wildlife teams, I encourage you to go to those. And yeah, we look forward to your feedback throughout the rest of the project.
Yes, and for those who asked wildlife-related questions, we will take the initiative to make sure that we pass those on to the whole team and the wildlife folks specifically. And ideally, by the time that their individual meetings happen, they'll be able to have an answer for you. So I've just put on some web links on the final screen there. The SNAMP website is on as a hot link, as well as the webinar evaluation survey. And to get to that, what you do is you highlight the link, and then you hit the Browse To button, and it will open it up in your browser. So we have a evaluation survey for this webinar. It would be great if you'd be willing to take that. I would also be welcome you to tell us now, just on the phone, since we actually have people on the phone, what worked for you for this webinar, and also what we could do to make future webinars better So first of all, does anyone have anything to say about what worked well in this webinar? I do see John saying well organized and clear. Thank you. Any other comments about what works well in the webinar setting?
I thought the slides and graphics were really easy to understand quickly, so thank you for that.
Thanks, Sue.
Okay, any other suggestions? Ideally, it looks like the rest of our meetings for the rest of the year will be in-person meetings. We've made a commitment to hold them in person unless we have low enrollment, and we put our cap at 10. And so I think for the Fire and Forest Health, we already have enough people signed up, so we're pretty sure it's going to be in person. And with that said, I'd just like to thank everybody for participating. Everyone did such a great job putting their phones on mute and asking questions at the appropriate time. And Maggie and Qinghua, what a fabulous presentation. So thanks to everyone, and I'll go ahead and end the webinar now. Thanks very much.